instance? Out of curiosity, who here has deployed a CoreOS instance? That's what I like to see. Awesome. We're going to be going through a lot of, just talking about kind of what's happening on the back-end side. We still have another minute or so I don't know how much that is tied to like the streaming stuff. I know like CCC, like you start when they say you start because, things work like clockwork, but. Oh, okay. Well then, I'm happy to get a little bit ahead of the game, for folks. That way, if there is things that back up a little bit more, they can reclaim that time. Absolutely. So, we will start with this. So, my name is Brian Redbeard Harrington. I work at CoreOS. I used to have a giant beard that hung down to my waist. There's this television show in the US called Duck Dynasty. Europeans, you probably haven't heard of it. That's a good thing. It's a bunch of, frankly put, racist jerks. And I was tired of being associated with them, so I hit the reset button. And now that it's kind of leaving the zeitgeist, I can allow it to come back. So just to give you a little bit more history, I've got to start by saying I'm a recovering Slackware user. I started out Slackware 4.0. 2.2 kernel was a wonderful thing, and it really kind of introduced me to Linux by just throwing me into the deep end of the pool. It wasn't like having to do the full bootstrap from scratch, but it was enough to kind of really introduce you to dependency hell and the following mantra, and that is configure, make install. And every package that you want to run or install at that point, circa 1997, that's what you do. Like, Patrick Volkerding, really not into binary package managers, at least at the time. So knowing that, or realizing that this becomes a bit untenable, especially if you want to maintain a system over time, I am not too proud to admit that I went a different path for a little while. And I was a FreeBSD user for a very long time because the ports tree took care of that dependency management while still giving me the ability to compile everything from source. And that was important to me at the time. But then, as hardware got faster and faster, you didn't really have to squeeze every last drop out in order to have a usable system. I went over to using Red Hat. And I was a Red Hat user / Fedora user for a very long time. I'm still a Fedora user right now. A lot of that was helped along by the fact that I worked at Red Hat for a very long time as well. I was on the consulting team in North America. For anyone who is not necessarily aware of the lineage of the Red Hat consulting team, Red Hat consulting is where when VA Linux kind of disbanded and broke apart, a la like the American Bell system, Red Hat gladly took in VA consulting, scraped the name VA Consulting off the door, put up a new one, and just kind of let it ride for a long time. And I was fortunate enough to work in that organization that had the lineage of VA Consulting attached to it. But we talked about kind of where that started, and the big thing if you're using Red Hat is you become used to RPM, and you become used to package managers in general. So Yum was kind of the solution to solving that dependency hell, and other distros, using DPKG on the Debian and Ubuntu side, used apt then to solve it. And then you start getting into things like Pacman and eBuilds and Portage and Emerge. And then you get to the point where a young bearded individual like myself takes off the fedora and moves to the center of the earth, which is CoreOS. Now, to tell you a little bit more just about CoreOS, there's a lot of folks here that have deployed it. There's a lot of folks that have not. CoreOS was started by individuals, especially early on, from a pretty okay lineage of folks understanding Linux. CEO came from Mozilla and Rackspace. The CTO came from SUSE. You know, the first employee was from Google. And, you know, we have a number of other Red Hatters there as well. That's just a little bit more of, but none of you came here to hear me give this history lesson. What you came here me talk about is specifically tool chains and how you actually do this bootstrap process of building a Linux distro. So in the case of you know, an RPM-based distro, it's the whole build system is Koji on the open source side of things. Really awesome tool for kind of managing a single package across a number of different architectures and guaranteeing that it gets built correctly. You know, there's similar tools with DPKG to do that, and most of the other distros have some flavor of bash glue. And from the previous theme, I am also not too proud to admit that CoreOS lives in a little bit of that bash glue. But to talk more about the CoreOS toolchain, one of the most important parts on the side of building the distro is a set of packages called Depot Tools. So Depot Tools was created by Google, and it's a, you know, they will say it's a Git workflow management tool. That's kind of what it is. There's a bunch of stuff in there as well for doing code review, using the Revolve like code review system. There's a lot of useful stuff. The biggest thing that we as CoreOS use out of that is this tool called Repo. And what Repo does is it allows you to manage a bunch of Git repositories at once. So now we can take and manage actual source trees, and developers on one project can just work on their own source tree, while developers on another project, you know, using like etcd, our key value store, and Fleet, a kind of systems abstraction on top of systemd that use each other. The Fleet developers can really just care about Fleet. The etcd developers can just care about etcd, and when they're ready to cut a release, they can do that, and each team can kind of manage themselves independently. It uses this kind of XML-based manifest, which I'm really not that jazzed on, but the nice thing about it is only a small number of people ever need to touch that, because a lot of it happens in the back end. So, you know, a copy of our manifest information is up on GitHub at github.com/coreos/manifest. To give you a little bit more of an idea of the types of things that you see when you go to do this, like repo sync, is, you know, you just start getting information where it starts ripping down information, you know, pulling etcd and locksmith, and goes upstream to Docker and grabs their stuff, and, you know, our init system, and, you know, toolbox and boot engine, and a bunch of other stuff. And this master XML file is just a manifest that breaks down and starts listing projects. So it will be like the basic name of the project, you know, the overall group that manages that project, the kind of subgroup, and then the name of the software. So a lot of this will be like GitHub for the project, because they're the overall host for a lot of our repositories. You know, it would be like kernel, where that way GitHub specifies a certain mechanism for how you retrieve the updates for that specific source control system, while the kernel says, hey, we are going to use git.kernel.org, because we use the upstream kernel, we push all of our patches upstream, and we run the current stable kernel. It's a little different than, you know, distros of my past, but it's a wonderful world to live in, to know that when I'm building this new image, I'm running, you know, 3.18.4, and I've got all of the newest hardware support. It's a little bit of an aside, though. But, you know, so the group is going to be something like, in the case of GitHub, it's going to be your organization. That's CoreOS, or that's .cloud, or, you know, et cetera. And then the software is the name of the package. Now, to get a little bit more into this, you know, we're talking about these remotes. So, like, with a remote name of GitHub, it says, hey, kind of jump up one directory from the overall path, and then use this general strategy for retrieving the information down. If you're using something like CROS, which we'll talk about in a little bit, you should retrieve that from https chromium.googlesource.com, and then their whole review process is using Garrett. So wait a second. You just see Chromium in that? Yes. Yes, that was in there. So on top of Depot Tools, Google wrote another really awesome piece of software. You know, it's a little bit of a travesty for all of their data mining and horrible things. Google does not get necessarily the rap that, or the commendations that they should for releasing open source software. But one other fantastic thing that they wrote was something called the CROS SDK. So it's used to build Chromium, you know, the laptop distro, but it is just an SDK. Like it's just a bunch of bash scripts which do things in a way that we, CoreOS, want to do them. Like we had this vision for how we were going to build this operating system and how we were going to push updates, and the CROS SDK happened to do that. So we were able to kind of be consumers of this open source upstream. In the same way that during the last talk, you heard this argument for use the upstream, push things into the upstream, converge on, you know, useful, meaningful, intelligent, common patterns. It didn't make sense for us to reinvent that wheel. Now, we don't use all of it, but, you know, we push patches where needed, and we consume the upstream as often as possible. So are we just a fork of Chromium? No. No, it's an SDK. Chromium is built from this SDK. We are built from this SDK. Chromium uses Omaha protocol as well, which, you know, I'll be going into a little bit later. But there are other forces at work. And this is something that we have started to hear an increasing amount. So I'm happy to have the forum to, if nothing else, throw Chromium under the bus here too. So using, you know, kind of a Git tree model, you've got CoreOS, where, you know, we are doing our own thing. You've got Chromium, they're doing their own thing. But there's this green dot over here. And there is a meta distribution at work. So we heavily use Gentoo ebuilds. We sync our own tree, and we maintain all of our own packages, and we consume some Gentoo packages directly, because the Gentoo ebuilds then reference upstream sources and tarballs. So it's this weird situation of, are we pulling source code from Gentoo? No. Are we pulling the equivalent of spec files from Gentoo? Yes. Do we maintain a bunch of those and patches them ourselves? Yes, and we, you know, keep all of those facing the public. So we're kind of back to this thing of, so why is this interesting if you're just a Gentoo fork? Well, we're not a Gentoo fork. As much as Red Hat is not a fork of Fedora, you know, there are a lot of individuals in this community that do really important work, and we're happy to be able to stand on their shoulders. But if we're just doing ebuilds, then let's talk a little bit more about what CoreOS is doing that makes us different. So we have a read-only user land, first and foremost. That means everything in /user is immutable. You cannot just even go in and do a mount-o read-write remount and start changing things. Like, we've found some interesting things that you can do with the GUID partition table to lock that down. And the idea is that you're going to be able to really force the user land into a state where you can always guarantee what's happening. And we're doing these atomic updates to the entire operating system. But on top of that, we're also building in a key value store and some things for containerization. So it really comes down to, if you are trying to run an application and CoreOS doesn't ship it, and chances are CoreOS does not ship it because we keep things as lean down as possible, it should be in some form of a container. Now, there's a bunch of talks here going on in the virtualization track tomorrow that I highly recommend folks see. Vincent Batts is talking about Docker. John Bull from the CoreOS team is talking about Rocket. If you're not familiar with kind of what's going on in containerization, it's a really fascinating realm. But the biggest takeaway is that we are not a general purpose distribution. Like, we get lots of folks going, cool, I downloaded Coreos and I installed it. How do I run WordPress on that? Ooh, well, you're going to have a hard time just doing the apt-get install HTTPD that you think you are, and there's no GCC, so you're not going to compile anything directly, so good luck with that. But what it means is that, we're opinionated about this, and we're comfortable leaving behind the general purpose land in favor of being a little bit opinionated. And this opinionation kind of gets into the update model as well. So, if you've got this read-only user land where you can't actually touch the overall content, you can't just read-write into it, like even through a remount, you have to have some mechanism for guaranteeing that you can update everything. So you've got to use our partitioning scheme, and I'll show you that in a minute and show you why you have to do that. Now, you can bring additional disks, but if you're going to boot off of SDA, we own SDA. All the other disks, go nuts with it. That's great. By all means, do that. But the way that we then make this happen is, so you have this giant set of partition tables, in the GPT. And the most interesting things here for you are going to be that we have two copies of this user A and a user B partition. And we define UUIDs for the partition type. But we're also using metadata on the GPT to start tracking a priority of which one of these is preferred, the number of times that we have tried to boot that partition, and the number of times that it's been successful. Which, when you're doing an atomic update, is kind of important. What happens if I go to push an update and it fails? What do? You have to have some recovery mechanism. So, given that we have these defined UUIDs that say, if your UUID is that, you are a CoreOS user B or user A partition. And if your UUID matches that string, you are a CoreOS user B partition. This is the same kind of methodology that Windows uses with the GPT or macOS uses with the GPT to be able to identify their partitions in the sea of partition possibilities. And again, that metadata allows us introspection into what has been happening with the host. So it is, there we go, OpenOffice crashing on me. I have to track down the LibreOffice guys to file my bug reports here. Let's recover. Let's jump down to where we were at. Seriously, I'm told 2015 is year Linux on the desktop. I mean, fortunately, I've been doing it for a decade, so maybe I'm just a little bit early. But so where we left off, we're talking about we've got these attributes sitting on the GPT, but so we've got this SDK, which, by the way, the SDK, bounce it over to the correct screen. I'll just show this real fast. So, you end up with a cheroot that you end up doing all of your builds actually inside of, and you are compiling everything from scratch for your architecture. And exactly as promised, we're using eBuild. So, if I wanted to go through and actually make some change to it, I can go through and say, hey, show all of my repo branches. So it's a little hard to see, but I have this one set called master, which is tracking the overall upstream. And then, you know, I've got this thing here where I'm doing some patches to our toolbox. So I created this branch for toolbox, and this is a branch that spans all of the Git repos that we're tracking. So if this particular fix needs to touch something in toolbox and needs to touch something in grub and needs to touch something in Docker in order to make that work, we can make all of those changes in the individual spots without having to kind of really get too deep into submodules and everything else in Git. And repo is pretty easy to use. I mean, if you understand git add, git commit, and kind of can wrap your mind around git rebase, you know enough to be dangerous with that and start making changes to it. The other side of it is that there's 3 basic stages once you get into the CROS SDK. 1, you have to do your repo sync. 2, you have to build your packages. So that's going to compile all of the individual sources. And in this case, we're going to make binary packages specific for our machine. And then we're going to build an image out of those packages. Because as I just showed you, we have this mechanism where you have a partition table that sits on a machine. And the concept of an image is now just taking and assembling everything into a specific flavor of what that overall image looks like. So that might be a QEMU image. It might be an OpenStack image. It could be a raw disk image, or even assembling it into an ISO that will really be read-only. So to do those, you will just, you know, go into the directory for all of the CROS scripts, and you know, I'm going to show you where you can find the full, like, detail, step-by-step walkthrough of doing every one of these things. Actually, I should just cheat and do that right now. So if you go to coreos.com/docs/SDK, we get into, oh, I don't actually have network connectivity in here. So that actually has 4 or 5 different complete sections on building production images, building development images, setting up your SDK from scratch, tips and tricks, so things like just shortcuts of showing you all the important UUIDs and application IDs for Omaha and the GPT. But so you end up in a state where you just use this to say, I want to build all of my packages, and I want to do this for a, you know, production image or a development image by scratch. And it will just go through, make sure that it has, or use all of the sources that repo has sucked down, and build everything individually. After you have done your build image or build packages, you would do a build image. Now, I did a build image here a little while ago. So you see, it actually just goes through and does an emerge of UDEV and dbus and all of these things directly into this disk image that it built way up above here. So it kind of lays out the actual partitions, tells you what you're doing. Recent change that we made, we have abandoned ButterFS. We had a good run, but you know, we've contributed what we could, but we needed to get back to ext4 for the time being, because at the moment we now have overlayFS to be able to use within containerization systems. So from there, we go through and we start emerging the binaries that we built previously into that disk partition table. And you know, we go through and remove some of the firmware that, you know, users are never going to need. We go through and we set all of our dmverity hashes inside of the actual image to make sure that you can actually verify and trust the content that is there. Then we go through and we generate some of our upstream tooling information so that we can just publish like a version.txt file. So this is really nice because we publish this onto all of our repositories to make it easier to both develop around CoreOS and write tooling where you can always depend on these basic text files to be there that you can suck in and use as environment variables inside of scripts to dynamically build everything out. So we've gone through and created this production image as CoreOS production image.bin, and then we're going to convert it to a virtual machine image using image to VM. So this now takes that disk image and imprints the idea of who it is on top of it. This is that process of saying, now you are OpenStack, you are a Hyper-V image, you are the ISO image. So we do that. In this case, I just built out a QEMU image, and we even generate a shell script so that you can spin it up real fast. So if I can see behind me, so it even will do the full process over here. So after I've done that, it's in my output directory. So build images, TMD64 user, and then we have developer. I have alpha. This is a brand new one that I built this morning. 130. Wow, I cannot see from this screen. Oh, okay. I just I tore down my SDK and rebuilt it for this to be able to do it from scratch. So if my authorized keys were there, it's going to inject that into the image using Plan 9 file system extensions. So it uses Plan 9 to actually share part of my host directory into that. 9p, yes. Yes, it is. Yes. Well, so that's one of those tricks where if you're running like rel 6, you're running a 2.6.32 kernel with things backported into it. So 9p is not something that the majority of users running Red Hat are going to need. If you're on like Fedora, or I think it's in rel 7, that would be fine. Rel 7 is 3.12 kernel, and we're 3.18.4 right now, I believe, because as most folks know, like the kernel doesn't break user space, and especially if you're running your content inside of a container. My eyes are awful, but I just saw your hat, your red hat. So especially when you're getting into Linux containerization, all of the containers are going to share that same kernel. So I've done a bunch of proof of concepts where I took an Cobalt Rack 3, which was running an AMD K62 processor. So it's it's still within the Intel architecture, and so it can use like an Intel kernel, and taken these programs that were written for a 2.2 kernel and run them on a 3.17 kernel at the time of testing. But this is the whole, that's building an image. You can follow the directions on the website. That's not that interesting. It's our version of RPM build, and it's our version of taking all of these things and kind of building a cheroot and doing a yum install of the RPMs into a cheroot. It's just the output of ours is an entire disk image. We don't give users the option to just kind of pick and choose components from within that. So back to slides, kind of the second half of everything here, if it will let me. Come on, LibreOffice. You just start closing out terminal windows and kill that. Come on. Okay. Try turning it off and turning it back on again. Yep, keep old styles, go down to Omaha, and we're back. Okay, so second half of this, talking about the Omaha protocol. So this is how we actually push out our updates to CoreOS. So Omaha protocol was created by Google specifically to handle updates to Chrome browser and Google Earth. You know, it was something where they needed a secure update mechanism to handle touching all kinds of different pieces of software. So within the Omaha protocol, you are providing an update to an application, and it doesn't matter what that application is. The client for the protocol is supposed to handle whether or not it's an update to a browser or whether or not it's an update to an entire operating system. So one of the things that we did is we wrote open source bindings in Go Omaha, which are repeated again a bit later. But to talk about Omaha is to first look at what their design goals were. And there's two very simple ones. One, they needed to provide a more efficient alternative to SSL as far as actually securing the content. And the second was that they wanted to use HTTP as the transport layer. HTTP is very easy to pass through firewalls and proxies. If the curl libraries are on a box, you can, or wget, you can expose environment variables that will allow any process to kind of navigate through those proxies. And equally important are design non-goals. So these are going to be things like you do not want to rely on SSL. So when we said, they wanted an alternative to SSL, SSL primarily gives you two things. It gives you assurance and it gives you privacy. The privacy is through encrypting content. The assurance is through guaranteeing that a user is allowed to run something or that the content has come from the individual that you think it's come from. Well, when it comes to the assurance or privacy, encryption matters if it's not content that is just publicly sitting on the internet. Now, while I would love to fill the NSA's deep packet inspection systems with just encrypted, publicly available, content that's hundreds of megs, it's a burden for like the CPU overhead for customers running a lot of this stuff, which admittedly we just push off to GPG. But as far as the assurance level, we found that it's a lot, and Google found it's a lot better to just rely on GPG itself. And the mechanism for handling that assurance is that you hash all your content, you sign the content, you sign the hashes themselves, and now you've got a mechanism where you can guarantee that content was not modified in transit. So you at least know that it's gotten down to you in a state where no one has touched it. Now, since we are pushing this entire operating system image, we can bake the public keys for the trust into the OS. So now the OS itself has all of the key IDs for GPG to be able to validate that the updates are actually coming from CoreOS. Because we have this mechanism where we push everything down to disk and you can't modify the content on disk in that partition, it means that you can have a much higher degree of assurance that everything has been pushed in the way that you thought it has. So the other idea that Omaha really stresses is the idea of keeping your updates fresh. So the idea is that it's a simple updater. It's polling for the updates, but as soon as the updates are there, the client pulls them down. So the client is in control of this. And more importantly, because of how it uses a semantic versioning system, the whole idea is that you can keep a user from being susceptible to downgrade attacks. So you always want to make sure that a user either is set to a forward image or falls back to the same image that they are on. Never goes back in time. That's how you avoid things like getting hit by Ghost after you've patched it, or Heartbleed, or Shell Shock, or any of these other things. Yes? Okay, I will try just doing it this way then. So, as I was mentioning, the whole idea here is to avoid having rewind or replay attacks. So, what it begins looking like with this atomic update is that a client will send an application ID down to the update server in an XML block, and it says, "Hi, I'm here, I'm running version 544. The server responds back saying, "Oh, 544 is a little bit out of date. We are currently running version 575. Here is an RSA signed signature of the content. Here is the date stamp of the file. Here's a location on a CDN that you can pull it down from." So the idea is that you want to be able to pull this out of band. You want to be able to push the content into something that can handle the distribution for you, aka, a generic HTTP transit system, and just give the client the URL where they can pull that down from. And since you're giving them enough metadata and signed content to be able to validate from that untrusted location that the content is good, you're able to work through things in a way where you don't have to worry about, like I said, content being modified in transit. Who cares if it's coming down from Google or S3 or even a local Nginx install. The client then downloads the data, verifies the hash and the cryptographic signature, and applies the update to the disk. Now, you remember earlier in that partition table, we had very specific geometries that were there. So we actually will go through and just completely overwrite that portion of the block device to be able to push the update down. The updater exits with a response code and reports that to the updates server after. So what's happening here is you're getting telemetry back and forth. You're getting information saying, step 1, here's the version I'm running. Step 2, I'm asking for an update. Step 3, I'm retrieving the update. So what this telemetry does is it allows someone running the Omaha server to get an overall picture of the ecosystem as a whole. Now, this is macro data, not micro data. So you're getting things like, I see that 20,000 machines are running version 544. I'm about to push version 575, and you can watch that number change over time, and you can rate limit it. Since it is this polling model where it's asking for an update, if the update servers are down, it's not a problem. This is similar to like satellite server inside of Red Hat. If your satellite server goes down, it's not like any of your infrastructure breaks. The failure case is you're just not receiving updates. So it also allows for rate limiting, because now what we can do is similar to a mobile provider where they're pushing out their over-the-air updates to Android. They can rate limit in such a way where you say, okay, we are not letting more than N number of machines update every M minutes. So we will allow one machine to update every 5 minutes to start. And so you can start to watch that trickle process, and the telemetry that's coming back tells you, okay, the system has gone through a full successful update, and now it's rebooted and it's running the new version. Or the system ran through that update and there was a problem and it had to revert back to that old version. Because using that A-B partition scheme, you can pivot between those. And just to let you know, I've got slides to talk about that next. But this is important because as much as you want to be able to guarantee that every update is successful, that's never truly going to be the case. So to talk about this, in our image, we started out and the OS is installed to the user A partition. We've got this giant data partition which resizes to the end of the geometry of that disk. So that is how you deal with things like cloud providers where they allow you to dynamically allocate the disk. It also just means that if you have administrators who are used to running in VMware where they just go in and randomly resize disks in order to try to fix things, this will handle that automatically for them and stretch the update out to the end of the disk. So a new update is coming down from the update server. It is staged to tempfs. It's unchecked. It's downloaded. We verify the crypto on it. Assuming that everything is good, we will apply it to the B partition. If that is good, great. Now we just run off the B partition. We're able to update the metadata on the disk, and we know which partition we should be running from. In the unlikely event that there is a problem, the update fails, we have a grub module which reads that metadata on the disk and can revert back to the old partition. We were running from the old partition before, so we know it's good, and the only thing that we're working with is changing the user land. So it puts you into a state where you're always doing fast forward updates, and the worst case scenario is that you are running on the version that you were already on. So it seems here, because I had packet examples of these showing the actual Omaha content. And it looks like when LibreOffice crashed, I did not save that, so I need to pull them from a different one. But while I'm doing that, I will go ahead and start with asking, do folks have questions about any of this? So yes, in the center there. Yes. Mm-hmm. Uh-huh. So let me ask one question here. So do I have to repeat the question so that? Okay. So the question was, given like an example of the Thunderstrike attack, which was announced at CCC, where you are actually relying on chain of trust or potential gaps in chain of trust, where because the public key is embedded in the actual image, if there's some way that you can do a binary modification to the underlying content where you're effectively injecting your own values in there so that you can force a new update in place. I'll say, so there's a couple things with that. One, what that is going to do is allow you to change kind of the state of the update. And at that point, you're going to have to change a lot of other things too, like where the updates are coming from and maintain that over time. The most likely scenario that's going to happen when you do that is that the box is going to crash on a reboot. So there is the potential for success there. That, like, I want to be completely clear that, like, this does not completely mitigate against that. This is something where if you have a highly motivated attacker, they will be able to get into it. In the same way that, now it's a different attack scheme versus just getting into a host and injecting your own GPG key in general. Mm-hmm. Oh, okay. So there's, okay, I misunderstood you there. So the actual install and update scripts actually contain the entire public key in there. So what you're going to have to do, like I'm going to actually enumerate for you the entire process that you have to do to exploit the vulnerability there. So what you would have to do is you would have to, one, get previous access to the system, and you're going to have to modify the contents of the disk directly. Once you have modified the contents of the disk directly to inject your own additional key, you're also going to have to either do a DNS spoof to get it to go to a different location where you have content that's been signed by your different private key, or you're going to also have to modify the update location in the configuration on disk. Because one of the things that we do allow to do is that you run your own private update server. This is for the like capital E enterprise customers that can't just accept public updates, so they need to slow things down. So they have an instance of our update server just sitting behind their firewall. So what the attack actually looks like in practice is similar to jailbreaking like an iPhone. It's something where you have to find some other vulnerability that allows you to get into the underlying block device and modify it directly in place to then install a permanent chain of attack there. So there's another question, gentleman in a polo shirt, gentleman in a blue shirt here, and then with glasses. So we'll start with gentleman in the polo shirt. Yes, we do. So if you set an invalid set of flags on the partition table, it forces it into a locked state where it just goes, I don't know what to do here. You know, we're working on a permanent set of patches where it's ratified into it, but it's just a party trick that we found at this point that allows for that to occur. Okay, so next up front here.
So modifying any block on the disk, wouldn't that be caught by DM Verity?
Yes, it would. That's why we started putting in DM Verity as well.
And the next question is, do you do incremental updates?
No, we do not do incremental updates. Everything is an entire atomic disk image. So then there was a gentleman with glasses there, and then the other gentleman with the glasses and the blue shirt. So. Yep. Yes. So because we are using the Gen 2 e-builds, within the Gen 2 e-builds, you can actually specify a specific Git commit that you want to use. So it doesn't even have to be a tagged version. You can just say, I want to use this exact commit. Yep. So I was doing a bunch of work after FaucetCon, really tiny open source conference in the US, where one of the sponsors gave out Minoboard Max, and I was actually using that to figure out the exact drivers and everything that we were going to need to support the Minoboard Max as an embedded platform, and that's exactly how I did it. I pulled a different kernel from the upstream, specifically said the exact commits that I wanted to use on that newer kernel, and then also used a custom configuration with the kernel to be able to add in all the additional drivers. You get your second question, and then we'll jump over to the other gentleman. Yep. Yes. Yes, it is. So we do not have things that mention explicitly removing content. I think we have some stuff talking about adding additional content. But I will also say real fast, most of our developers are in #Coreos on Freenode. So I will throw A.B. Crawford under the bus, and he can help you out with that one. So, gentleman in the blue sweater. Yes, a reboot is required. So this gets into that whole, we are opinionated in how the types of workloads that you should run. You know, this is really geared towards situations where you tear down and rebuild machines all the time. Situations where your application is stateless across a number of hosts so that you can do a rolling reboot. And one of the things that we have there to help out with that is using etcd, we have a tool called Locksmith, which gives you a semaphore for reboots across an entire cluster. So you can guarantee that no more than n number of machines go down for service at a given time, where the administrator can define that. By default, it's 1, but you know, some of our users that have 5,000 machines or more, like rebooting one at a time isn't really an acceptable frame to do that, because it's just going to take you way too long. Yes, gentleman in the scarf, and then we'll go back for another one.
If rebooting is part of the plan,
Mm-hmm.
why bother with installing to disk at all and just not run the whole thing from memory?
Aha, so that gets into a lot of our users actually do that. So a company called MemSQL does all their QA testing where they load the image via Pixie and just run it from resident RAM. And their update model is just, they have a process that watches our repos. When a new update gets published, they just wget it down and they reboot the machine. It picks up the new configuration from Pixie and just runs. So there is some docs. Rackspace also uses it with the OpenStack project Ironic. So Coreos is the basis for, Jay Falconer of the Rackspace team built out a system, or was a part of a team building out a system called Teeth that uses CoreOS running in resident RAM, where they have added in an Ironic agent. So it calls home to the OpenStack APIs. So you can use the OpenStack Nova APIs to, the Ironic APIs to deploy a physical machine in the same way that you would a virtual machine. Ah, okay. Okay, so I was looking at Jay's code a little while ago, and I was a little bit confused because coming from Red Hat, IPA to me means Identity Policy Audit. So I was sitting there looking, oh man, they're getting real weird, including all that stuff too, but that makes... Okay. Yep. It is licensed Apache 2. It is written using Go. So that's one of the things. CoreOS does not ship any interpreted languages with the exception of Bash on the underlying user land. So it means that you don't get Python, Ruby, Node, Perl, none of that. And it has meant that for things like, so we use Cloud Init very, very heavily. We use Cloud Config. So one of the major peeves that I had was that a customer of mine, because again, when I worked at Red Hat, I was on the consulting team, they would have a whole long curated set of kickstarts for all their physical machines, and as soon as they wanted to move to some cloud system, they had to now rewrite all of that into Cloud Config. So what we did was Cloud Config is the configuration manifest. It's the configuration manifest if you're on bare metal, if you're on like bare metal installed to disk, Pixie, cloud platforms. And what we do is for the bare metal machines, you actually provide it as a kernel boot option. So you say, cloud config URL equals, and then give it an endpoint, HTTP endpoint, and it will retrieve that and then use that for the manifest in running, which is how MemSQL does their configuration and all of their QA testing, because they just have, an Apache server sitting there with these YAML definitions. Now, what that means is that we had to rewrite Cloud Config in Go, and we have to maintain a tracking implementation of someone else's spec in a different language, which, on the one hand is really annoying, and that's putting it lightly that it's annoying, but it also has been interesting because we've had a lot of folks come to us going, hey, I'm working on this embedded platform, and I need to figure out how I can strip this Go binary down even a little bit further, because now I can run this on my embedded platform, and I can use Cloud Init to configure this embedded platform, and I don't need to bring all of Python with me just to support that. So, yes? Mm-hmm. Yes, and we have everything to do config drive with that. So what we do is we actually look for a disk named config2, and through the wonders of systemd, we actually auto-mount that based on name, and then we have units that look for the presence of a file at that exact path and pull it in. So that's, you intuited exactly what we do. So we are getting dangerously close to time. I think I have time for one more question. Yes? No. So we have all of the images that we have ever created published on the kind of content repository that we've got, going back to, I think, yeah, they're all there up on the.
Is there like a crash flag that you can add in your disk metadata to sort of like, this one crashed a whole bunch of times, maybe it's not so good, or?
It's not something that I think we've considered, but it's not necessarily a bad idea either. The only issue becomes like modifying those images after the fact to add kind of a crash flag.
You said something briefly just earlier about how you make it hard to go back because you don't want to regress on some
Yes.
day or something?
Yes. Well, that is part of Omaha protocol with how they push updates. So if I staged if I logged into a machine, wgetted down an old image and ran Coreos install, kind of forcing a target against that, you can force it into place, but it is non-trivial. Like, it's definitely kind of an absolute disaster recovery mechanism that you'd have to. It does not. You have to force it by. It is not any kind of automated fashion. You have to have access to the system, have root on the system, like, and escalate through a whole series of processes.
My issue is potentially if you have a bleeding brand new kernel,
Mm-hmm.
stable, maybe there are issues that you notice over time.
So reasonably, what the answer to that is? Okay, sorry, time's up. I will talk to you offline about that. Thank you so much for the time. We have a table over in the AW hall, so if folks want to ask questions about this or Rocket or any of the other stuff that we're working on, feel free to grab me. Thank you.